Large CNC machining is not only about handling bigger parts. It is about controlling heavier materials, longer structures, and tighter tolerances across distances measured in meters instead of millimeters. To do this reliably, material selection becomes one of the most important decisions in large-scale machining. Carbon and alloy steels are widely used for structural components such as press frames, crane booms, and heavy shafts. Materials like A36 and 1045 provide strength for large machine structures, while alloy steels such as 4140 and 4340 offer higher tensile resistance when parts must withstand twisting loads and repeated stress cycles. In aerospace structures, aluminum alloys such as 7050 and 7255 are selected because they combine strength with reduced weight. Aluminum-lithium variants improve stiffness while lowering overall mass, making them suitable for satellite decks and large aircraft components where weight directly affects performance. For harsh environments, stainless and heat-resistant steels become essential. Materials such as 17.4 pH stainless and duplex stainless resist corrosion in offshore and oil and gas systems, while high-temperature alloys like A286 and Incolloy 800 maintain stability inside power plant equipment exposed to extreme heat. Titanium and superalloys are used when both strength and temperature resistance are critical. Titanium 6-4 provides an excellent balance between low density and structural strength, although it is difficult to machine because it generates heat quickly and increases tool wear. Superalloys such as Inconel 788 and Hastelloy X remain stable even under extreme exhaust temperatures, but they place significant load on machine spindles during cutting. Large CNC machining supports industries where component size and reliability cannot be compromised. In aerospace manufacturing, wing spars extend across several meters and must remain geometrically stable to reduce fatigue over time. Landing gear beams are machined from high-strength steel and must maintain parallel sidewalls within extremely tight tolerances to prevent vibration during landing loads. In the energy sector, turbine casings the size of small vehicles require flat mating surfaces to contain internal pressure safely. Wind turbine hubs weighing tens of tons must align blade bolts precisely to avoid imbalance during rotation. Construction and mining equipment depend heavily on large machining systems. Injection molds for rock truck bodies extend across long spans, while excavator frames require precision boring operations to maintain alignment between pivot joints and hardened bushings. Marine and offshore applications also rely on large CNC machining. Propeller hubs made from nickel aluminum bronze are finished from rough castings with complex surface geometry, while subsea housings for remotely operated vehicles require precise sealing grooves that protect sensitive electronics under high pressure. Defense and space systems demand even higher levels of structural accuracy. Launch vehicle bulkheads combine ribs, pockets, and curved flanges within single forged structures that must remain stable through cryogenic temperature cycles. Large armor plates for land vehicles are machined with traveling column mills that maintain flatness without introducing distortion. One major advantage of large CNC machining is single setup accuracy. Because the entire workpiece can be clamped once, positioning errors caused by multiple fixture changes are greatly reduced, improving geometric consistency across large surfaces. Another advantage is part consolidation. Instead of assembling multiple smaller components through welding or fastening, engineers can machine complex monolithic structures from a single billet, reducing assembly time and improving long-term reliability. Large CNC machining also shortens production timelines compared to traditional manual methods. Components that once required months of template-based finishing can now be simulated digitally and machined within predictable production schedules. Surface finish consistency improves as well. Digital tool paths repeat with high precision across multiple parts, ensuring dimensional stability even during long machining cycles or operator shift changes. Not all large components are metallic. Composite panels used in motorsport structures and aerospace assemblies can be machined with diamond-coated tools to achieve clean edges, while industrial plastics such as UHMWPE are used for liners that resist abrasion and reduce friction in bulk handling systems. Maintaining precision at large scale introduces additional challenges. Aluminum structures expand significantly with temperature changes, which means even small thermal variations can shift hole positions across long panels. To control this effect, many facilities maintain strict climate control or update offsets using reference measurements before machining. Machine rigidity also becomes critical. Large gantry columns weigh several tons, yet still experience flex during cutting operations. Engineers improve stiffness by filling structural cavities with polymer concrete and isolating machines from floor vibration caused by nearby equipment. Metrology systems play a central role in maintaining accuracy. Laser trackers measure coordinates across large structures with extremely fine resolution, portable measurement. Arms verify features inside deep pockets, and in-process probes confirm geometry between machining passes to prevent repeated lifting and repositioning of heavy components. Large CNC machining succeeds when structure, material selection, measurement systems, and process planning work together as a coordinated system. Only then can machines produce oversized components with the precision required for aerospace, energy, marine, and heavy industrial applications. If you're not following now, you may not find this explanation again.